in the last lecture we learnt about what is a random experiment. Once we define what is a random experiment, we introduce the notion of a sample space. A sample space is a set of all basic outcomes of the random experiment. And we also introduced what was an event. Now, we quickly realize that the sample space and events are sets. So, once I define them as sets, that is when I define all the set possible collection of all basic outcomes as sets, I introduce the notion of basic set operations on these events. So, we notion of union, intersection and complement of events. A word of caution here is we do not view them as sets, that is a word of caution here is we are not interested only in the mathematical representation of these events as set, but we need to understand why we are using them as sets, and we need to actually articulate the situation we are facing in as these sets, as union of sets or as intersection of sets. Then finally, we looked at how we represent these sample spaces and events using Venn diagrams. The reason this representation is useful for us is when we are trying to find out the probability of events, that is our main purpose, and we are able to express a particular event as union or intersection of events, then how would we apply these fundamental concepts to actually work out or actually compute probability of events. So, in today's lecture, we are going to look at mainly the development of what we call the axiomatic approach to probability, or simply put, we would look at certain properties of probability. But even before I set up this properties of probability or the probability model as some books name it, I will just briefly touch upon what have been various interpretations of probability. But I am going to only focus on three main interpretations of probability. One of the main interpretations and most popular interpretation of probability is what we term as the classical approach. Now, this classical approach is also referred to as a priori or theoretical approach to probability. So, what this approach says is let S be the sample space of a random experiment. We have already introduced what is a random experiment and what is a sample space. But here we are trying to say in which there are n equally likely outcomes. So, we are talking about what we mean by equally likely outcomes. Now, certain examples, natural examples of a equally likely outcome is when we refer to what we call a fair coin and we toss a coin, we expect the head and tail, which are the outcomes of the toss of a coin, to be equally likely. That is, I expect head to occur as likely or equally likely as a tail and vice versa. Similarly, if I roll a fair dice, a 6-edged or 6-sided die, okay, which we use to play. So, this is how a 6-sided die would look. So, when I roll a die, I would expect any one of these outcomes, which are namely 1, 2, 3, 4, 5 and 6 to appear equally likely. So there is a chance of me getting any one of these outcomes are the same. That is what I mean by equally likely outcomes. So, when I have an experiment when my outcomes are equally likely and an event consists exactly m of these outcomes. For example, again let us roll a die or roll a dice. My sample space here is going to be 1, 2, 3, 4, 5 and 6, and each one of these outcomes are equally likely. Let me define my event to be the event of getting an even number. So, the outcomes that satisfy this event are going to be 2, 4 and 6. The number of outcomes in this event are 3. So, the probability of getting a probability of E, which is same as probability of getting or rolling an even number by the definition of classical probability equal to m by n equal to 6, which is the total number of outcomes in my sample space. The number of outcomes which satisfy this event equal to 3, which is equal to half. So, my classical probability approach to compute the probability of an event is equal to 1 by 2. I can extend this notion and I can apply it to various examples, but one thing we need to understand and be aware of and always remember is this approach assumes that all of the outcomes are equally likely. The next approach, which is also a very popular approach, is termed as a relative frequency or empirical or a posteriori approach or interpretation to probability. What this approach tells us is the probability of an event in an experiment is the proportion of times the event occurs in a very long series of independent repetitions of the experiment. Let us understand what this statement tells us. Suppose my experiment is to toss a coin. Okay. So, I am tossing a coin. Okay. So, my first experiment is toss a coin. So, I am noting down the experiment, the outcome. So, suppose I toss a coin once and I find a head, I note down a head. I toss a coin twice, this is also a head. I note down the number of heads is equal to 2, number of tails equal to 0. I toss a coin thrice, I note this. Now, what happens is this becomes 2 and a 1. The fourth trial I get a head again this changes to 3, 1. So, suppose I continue to do this experiment and I get the following results. Now, this can easily be replicated by any one of us. We can take a coin and keep tossing the coin. So, here in 10 tosses I find 1, 2, 3, 4, 5 heads and 1, 2, 3, 4, 5 tails. I repeat this experiment. So, I can just go to 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So, if I keep repeating this experiment and I get a head, head, tail, 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 head, head, tail, head, tail. So, now the number of heads I have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and my tail is also 10. Okay. But will this pattern always occur? Need not be. For example, I could have a completely different, suppose another person is tossing 20 tosses of the coin and they just randomly, this is the sequence they get a tail, head, tail, tail, head, head, tail, tail, head, 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 tail, head, head, tail, tail, head, head, tail, tail. So, here if I count the number of tails, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 and number of heads is 11. Okay. So, imagine that instead of doing this experiment just 10 times or 20 times, I am doing it 1,000 times. Then it could be very well possible that I am getting 469 heads, I am doing it 1,000 times and I am getting 531 tails. I repeat it 10,000 times. So, we are counting the number of times. So, what we mean is we are repeating the setup independent repetitions. So, the first time I repeated 10 times, the next time I did it 20 times, then I made it 100 times, then I made it 1000 times, then 10,000 times. So, you can see that what this refers is to this n. If I am repeating this experiment infinitely, theoretically infinite number of times, okay, and I am counting the number of outcomes that satisfy a particular event. So, that event could be coming either head or tail. So, if I have 469 in 1000 turns, so my probability of getting a head is going to be the limit as this tends to infinity. I keep repeating the same experiment, and we can see that as this number increases or tends to infinity, this tends to a particular value. So, this is what is popularly referred to as the relative frequency frequentist approach or the empirical approach to compute probabilities. The disadvantage of this approach to computing probabilities is we are expecting that the experiment can be repeated for a very long period, but not really all experiments can be repeated in this fashion. However, this idea is if I repeat a particular experiment independently and n is the number of times E occurs in n repetitions, then probability of E is limit n tending to infinity, number of times this particular event occurs to the total number of repetitions. So, this is the next approach. We started with the classical approach and what is the relative frequency approach. The third approach is what we refer to as the subjective approach. Now, this approach is basically it assigns a best guess by a person making a statement. Very often we see people making statements like this: a 30% chance that it would rain tomorrow, or there's a 75% chance that a person would win a particular election even though that person is standing for an election for the first time. So, the statements of this kind actually measures an individual's degree of belief in a particular event. So, this type of interpretation or this interpretation of probability is referred to as the subjective interpretation of probability. Now, these interpretations have been popular for a long time, but then afterwards there has been a unified framework to interpret this entire probability theory, and that is what is popularly referred to as the axiomatic approach to probability. Going deeper into the mathematical framework is beyond the scope of this course, but however we are trying to give you the foundations that are essential for you to help you understand the statistical inference course. So, what is an axiomatic or what we refer to popularly as the probability axioms? So, let us go back to our random experiment. We learnt what was a random experiment. Let the sample space of my random experiment be S. So, sample space is given. What is the sample space? The sample space is S. And what we know is an event is a subset of a sample space. This is what we have already learned. Now, associated with every event, I am going to associate a number and I denote that number with this notation P of E, which is spelled out as probability of a event E. And what are the properties or axioms that this P of E has? The first axiom is for any event, the probability of the event E is a number between 0 and 1. That is 0 is less than or equal to probability of E is less than or equal to 1. This is what I refer to as my first axiom of probability. Now, the next axiom of probability is the probability of the sample space is equal to 1. I symbolically write that as probability of S is equal to 1. In other words, what this means or what this signifies is the outcome of any random experiment will be an element of the sample space. So, if I toss a coin, what are the outcomes? Head and tail. So, both these outcomes are elements of the sample space which I am going to tell. So, I cannot have an outcome of an experiment which does not belong to my sample space. The sample space is the collection of all outcomes. So, that is why probability of the sample space is equal to 1. The third axiom states that if I have a sequence of mutually exclusive events, we have already defined what is an event, and we also know that I can construct events given simple events. By simple events, I am just talking about singleton sets. I can construct a lot of events from simple events. Then what the third axiom says is the probability of the union. When I am taking union 1 equal to infinity, I am assuming that there are many events, countably finite events. Now, these notion of countability and finite events and everything are something you would be learning in your math courses in due course. I will just tell what is essential with regard to this course. So, what this axiom says is the probability of the union is the sum of the probabilities when I look at a sequence of mutually exclusive events. This is crucial for us to understand that what this tells is if I have mutually disjoint event. So, for the purpose of this course, I am just going to look at the finite union, even though this applies for a larger or countable union. We are not going into the mathematical foundations of understanding that at this point of time, but for this course, I can state the third property as the probability of union of disjoint sets is equal to the sum of probabilities. Let us look at only finite union. What does that mean? Suppose I have E1 and E2 as disjoint sets, then I can represent the union of these sets by. So, what does this mean? Suppose I have E1 and E2 which are my disjoint set. I know the union is represented by E1 union E2. So, the union of these disjoint sets is E1 union E2. The probability of the union is probability of E1 union E2. It is equal to the sum of probability. So, this is equal to probability of E1 plus probability of E2. This is what my statement or third axiom tells me. So, what is the understanding and why is this property important? It states that if E1 and E2 are two events that are disjoint, in other words, they cannot occur simultaneously, then the probability of the outcome that the experiment is contained in either E1 or E2 is equal to the sum of probabilities that is in E1 and the probability that it is in E2. Okay. So, this is what is the probability of union of disjoint events. For example, let us again take the case of rolling a die. I know this is my sample space. Suppose I define E1 to be the event of me getting a odd number, then I know the outcomes are going to be 1, 3 and 5. If E2 is the event of getting an even number, the outcomes are 2, 4 and 6. I know E1 and E2 are disjoint, that is, I cannot have an event where I can get an odd and even number in the same throw of a die, but I know that if I define an event that the outcome is either an even or an odd number, then the probability of getting either an even or an odd number is equal to the probability of E1 plus probability of E2, which is 3 by 6 plus 3 by 6, which is 1, which is nothing but the probability of your sample space, which is equal to 1. So, this is what we refer to as the probability axioms, and these 3 axioms help us. From these 3 axioms we get hold of many other properties of probability, and that is what we are going to see now. The first property of probability is, remember when we talked about sets, we talked about union, intersection and complement of sets. So, can we work out what is the probability of a complement of a set? Now, when we look at a complement, so if E is a event, E complement is its event, we know the first thing we need to understand is E and E complement are disjoint. Why is this true? By the way we define, E complement is the set of outcomes that are not in E, hence E and E complement will not have anything in common. These two sets or these two events are disjoint or mutually exclusive events. Now, another thing which we notice is E union E complement is your entire sample space. So, given an event E, I know first E and E complement are disjoint, and the second thing I observe is E union E complement is my entire sample space. Now, if E and E complement are disjoint, then I know that from my third axiom, I know the probability of E union E complement is probability of E plus probability of E complement. This is through axiom 3. My axiom 3 states that when I have disjoint or mutually exclusive set, the probability of the union is the sum of the probabilities. Now, axiom 2 states probability of the sample space is 1. So, my left hand side says that probability of E union E complement is probability of E plus probability of E complement. My right hand side states probability of S equal to 1. I equate these two to get probability of E plus probability of E complement equal to 1, which gives me probability of E complement equal to 1 minus probability of E. So, that is what we have, and we can. So, hence I have probability of E complement which is equal to 1 minus probability of E. Now, the next important property is we also defined what was a null event. A null event is an event which has no outcomes. So, I can define what is a null event. This is an event which has no outcomes. So, when I am defining a null event, then I am interested in knowing what is the probability of the null event. That is the next thing which we are interested in knowing. So, what is the probability of a null event? Now, what is the complement? I know the complement of my sample space is the null event. Sample space is the collection of all the outcomes. Null event does not have any outcome. Hence, the complement of the sample space is my null event. I know from my earlier property, probability of a sample space, the complement equal to 1 minus probability of that event. Sample space is also the entire event. Okay, it is a set. And my axiom 2, from axiom 2, I know probability of my sample space is 1, which gives me probability of S complement is 1 minus 1, which is a 0, but I recognize S complement is my null set, hence probability of my null set is 0. So, these two properties have been derived from the axioms or the 3 prime properties which we stated earlier. Now, the next thing is what we refer to as an addition rule in probability. The third axiom says very clearly it needs both E1 and E2. If I am talking about more events, one qualifier in the third axiom of probability was these events were mutually exclusive or disjoint. That was the important qualifier we had here. But sometimes we are having events. For example, if you recall our card example, one of the event I defined was a king of hearts. The second event we defined was hearts, okay. And then afterwards you can see that these two events, this had 13 cards, this had only one card. The third event we defined was a king. So, this had 4 cards. E2 and E3 had one card which is in common, and that was a king of hearts. So, you can see that many a time we have events which are not disjoint or which are not mutually exclusive. So, the natural question to ask is, how do I compute the probability of the union? So, why would I be interested in this? So, if you go back, my E1 was king of hearts, my E2 was a heart, my E3 was a king card. So, if my question is what is the probability that I have, I draw a card, what is the probability that I either have a heart or a king? This is the probability I am interested in finding out, but now E2 and E3 are not mutually exclusive. I know that they are not disjoint. How do we find the probability of such an event? This event is a legitimate event. This event is what is the chance that the card I have picked is either a heart or a king. How do we compute these probabilities using the properties which we have just studied? That is the question. So, the addition rule helps us to find out these probabilities. What does the addition rule state? If I have two events which are not necessarily disjoint, then the probability of the union of these two events is probability of E1 plus probability of E2 minus probability of E1 intersection E2. So, if they were disjoint, this would have been 0, and this reduces to probability of E1 union E2 equal to probability of E1 plus probability of E2, which is what we started with, and this was the third axiom. So, the addition rule is a more generalized rule for finding out probability of union of events. So, let us try and prove this rule using our basic properties of probability. We represent this. So, I have an experiment, I have a sample space. We saw that we can represent the events and the sample space using a Venn diagram. So, this block, so if I can, so the red circle represents my, so if you look at it, the purple circle, I will shade the area, the purple circle is my E1. The yellow is my E2. So, the yellow, let me shade it again. So, the yellow shaded region is my E2, the purple shaded region is my E1 and the orange shaded region is by E1 intersection E2. Okay. So, we see that the E1 and E2 are not disjoint and they are not mutually exclusive, but I have a theorem or but I have an axiom which says probability of E1 union E2 union E3 equal to probability of E1 plus probability of E2 plus probability of E3, provided they are mutually exclusive or disjoint. So, what I am planning to do is we recognize that this E1 union E2 is this entire shaded region of the purple, orange and yellow shaded region. I write this entire shaded region as the following. I write it as 1 union 2 union 3, where 1 and 2 and 3, as you can see from the Venn diagram, are disjoint. I do not have anything common between 1 and 2. I do not think I have anything common between 2 and 3, but I can see that E union E1 union E2 can be represented as 1 union 2 union 3. In other words, I am representing the union of E1 union E2 as the union of 3 disjoint regions or disjoint sets. Now, similarly, if I look at the same Venn diagram, I see that E1 can be represented as 1 union 2, E2 can be represented as 2 union 3, and I also see that the orange region, which is E1 intersection E2, is 2. So, these are the things which we can see from the given diagram, and that is what we have typed. We have here, that is E1 union E2 is 1 union 2 union 3, E1 is 1 union 2 and E2 is 2 union 3, E1 intersection E2 is 2. Now, what are we interested in finding out? We are interested in finding out probability of E1 union E2, which is the same as probability of 1 union 2 union 3, and I can apply axiom 3 to this, and I know this is probability of 1 plus probability of 2 plus probability of 3. Let me label this as my first equation. Similarly, probability of E1 is probability of 1 union 2, again through application of axiom 3, I get this is probability of 1 plus probability of 2. Probability of E1, E2 is probability of 2 union probability of 3, which is probability of 2 plus probability of 3. Let me label this as 3 and this as 2, and I have probability of E1 intersection E2 is probability of 2. I am labeling this as 4. In other words, I have just expressed probability of E1 union E2, probability of E1, probability of E2 and probability of E1 intersection E2 in terms of probability of 1, 2 and 3 by applying the axiom 3. Now, let us re-express this probability in terms of E1, E2 and E1 intersection E2. Probability of 1 plus probability. So, if I look at probability of 1 union 2 union 3, I have this is probability of 1 plus probability of 2 plus probability of 3. This comes from 1. Now, 2 from 2 I have this is equal to probability of E1, okay, plus probability of 3. But probability of 3 is nothing but probability of E2 minus probability of 2 this comes from 2. So, I can write this as probability of E1 plus probability of E2 minus probability of 2. Okay. But I know from 4 probability of 2 is equal to probability of E1 intersection E2, and hence I can replace this with probability of E1 intersection E2, and this actually tells me that probability of E1 union E2 is equal to probability of E1 plus probability of E2 minus probability of E1 intersection E2. This is what is referred to as the addition rule of probability. That is, I repeat, if I have two events E1 and E2 not necessarily disjoint, then the probability of the union is probability of E1 plus probability of E2 minus probability of E1 intersection E2. So, the key is to write the union as a union of 3 disjoint sets and apply the axioms of probability to show that the probability of union is the probability of E1 plus probability of E2 minus probability of E1 intersection E2, which we can actually prove from whatever we have seen.